an SPI serial port. Okay? And this last question. I'm going to try to get you all clear on this last question because it is just an introduction question to SPI. So you will not understand everything as you're doing this question probably. But this table is helpful and we'll come back to it. Also note, I tried to print this out this morning. It just did not copy well. So I think it's just best, due to the colors and everything, to just view this here. Okay, let me show you where I'm at. If you go to lecture handouts, I haven't put a lot up here, but there's a few lecture handouts up there. And SPI serial port introduction. So check out this guy and probably want to, you want to zoom in here or you like open it up in Adobe Acrobat or whatever. Yeah, when I make these in MATLAB, those fonts are really tiny, especially when you cut and paste it into a Word document. Sorry about that. Anyway, you can zoom in and see these things. But the main thing we want to see are the ones and zeros going across in this serial port. You can, of course, convert that to decimal easily with Windows calculator. But anyway, what we need to do now with this SPI serial port is transmit data from one device to another device and also read data from that other device into our processor, right? And what you're going to find is there's going to be a master and a slave. And we'll understand that here as we get going. The reason here, this document that I give you has 4 modes, and that's what I'm going to talk to you about. Make sure you understand that. You're going to be asked in the homework which mode is the diagram that I gave you. Now, by looking at these, you'll figure it out. Actually, it's very difficult to just look at the scope when you scope SPI to know what mode it's in, actually. Sometimes it's easy, sometimes it's not. These little dotted lines give it away for you, okay? So we'll explain what those dotted lines are. But first, let's give a general overview for what we're doing with SPI now. I'll come back up to that diagram. So we now, a lot of things, even microphones and speakers and all these things that we need to talk to in a cell phone and all this, the IMUs, all that, they're all digital transmissions. You know, monitors, your old, TVs used to be all analog, okay? Meaning there was a voltage change. And what was coming over your, over the airways was a value between, 0 and some larger range of voltage. And you had to sample that, even in like a video, camera, right? The old PAL cameras, the NTSC cameras and all that. That was all analog signals. And they were sampled by ADCs. Very fast ADCs. Well now, because they can put stuff really small, they put the sensor in the chip, like for an IMU. They put the sensor in there, and there's a little processor they put in there that's sampling that with ADCs or whatever, and digitizing that, and then sending it to us digital. Why do they do that? Well, that sending part of an analog signal always is susceptible to noise, right? We get interference on there, and that always messes. That's why, old TVs, you saw it, well, it's still today's TVs too. We can still get noise, right, and see garbled pictures and all this kind of stuff. But if you keep the analog part in a little chip, the amount of interference is usually a lot less than if you send it over long wires, okay, that analog signal. So a lot of things do the little sensing right on board on the chip and then send the data to you digitally. There's all sorts of different serial ports out. You guys know about all the different serial. There's USB, there's SATA for your hard drives, there's Ethernet and all this kind of stuff, right? There is a bunch of different serial ports out there. Thunderbolt and all this kind of stuff, right? Those are super complicated serial ports. This is a much cleaner serial port and used for small wires, small lengths of wires, I should say. That's how it can be simpler. When you start going over long wires like Ethernet, you have to have a way to correct for errors. Okay? there always can be data that's transmitted incorrectly, and if it does, you have to resend it and all this kind of stuff. Okay, it depends. I mean, if you talk about UDP, you just send and hope it gets there. Anyway, but with short wires, we can have a little bit less complex serial ports to help us talk from one chip to another chip. And so what you're going to see me drawing when I talk about SPI a lot is, again, our F28379D processor. And then a part of this processor is the SPI peripheral. Actually, there's 3 of them. There's SPI A, B, and C. I think we're going to be using B, but either way. Now, what this has now, you're going to set up some of the GPIOs to, instead of being GPIOs, one of them is going to be called chip select, or sometimes they call it slave select. So what we're going to find is the SPI on the 28379D, we're going to set it up as the master. And so that's why they call this pin slave select. When it gets pulled low, it's selecting a certain slave. Okay? And we'll explain that. Then, also, there is a master out slave in pin. There is also a master in slave out pin. And finally, a clock pin. S-clock, they call it sometimes. You know, each chip manufacturer calls these things a little different. You got to watch it to figure out what they call. Some are just SCK for S serial clock, all those kind of things. And then what you have is you have multiple chips out there that you want to talk to usually. Now, in your homework, in homework 3, when I get it finished, we will just be talking to one chip, so we don't have to worry about as much. But you can have this one SPI serial port talk to many chips. How does that work? So each of these chips out here are slaves. So slave 1, what we're going to be working in homework and in lab, the MPU 9250 is a IMU chip. There's another chip that I use a lot, and I don't know if we will this semester, the LS7366. So it's just some device out there that a company makes is what I'm trying to get across there. Okay? Each of these slaves have their own chip select, or I'll call it slave select. And you'll see it like this, slave select active low with a bar over it. That means for this device to be on, or whatever, be communicating, it's always on, but to communicate with the master, you have to pull the slave select pin low to ground. Okay? Normally it's hot. Normally you want it not communicating. All right? And then it should have labeled, sometimes they label a little different, but they also call their pin master out, slave in, master in, slave out. Now, some manufacturers will call it this guy. They'll switch they'll call it SIMO too. You may see it that way, or SOMI. Right? Same thing. Anyway, it's always a little confusion there too. And then a clock, serial clock. And this guy will have the same thing: master out, slave in, slave out, S clock. Okay, and now the wiring this. I mean, we could have 4 or 5 chips out there on this same serial port if we want to. So the wiring is actually very simple. We just take the master out pin, slave in, and daisy chain it, or just take it down and connect to those chips. All their master out, slave in pins. Well, they only have one. And then the master in, slave out, daisy chain down to there, and the same with the S clock. So using those same 3 wires for all the chips you're talking to, the only thing that's unique is this slave select. Okay? So you need, if you're talking to 2 chips, you need to have 2 slave selects over here on your 28379D. And now the nice thing is, even though we think of it as a slave select, we're just going to keep it as a GPIO. So I think it's GPIO 65 we happen to use for the slave select of the MPU 9250. Okay? But it could be any GPIO that you choose. That's the one that's wired to it by me. Okay? Then, to talk to this other chip, we would have to have another GPIO. Maybe GPIO 52. I think that one's free. That one could go to this slave select. Okay? And so what has to happen, and this is done by you and your programming. You know how to pull GPIO 65 high and low, don't you? GPIO data regs dot, what would it be? That's probably GPC, I think so. GPC set or clear dot bit dot GPIO 65, right? Just like we turn on and off an LED. We can turn on and off the communication to this slave chip, okay, by pulling it low. When we're done with the chip, we're done communicating with it, we pull that pin high. Okay, saying, I'm done with you. Go back to whatever you were doing, right? Collecting in data for me or whatever. Same with this chip. Whenever I want to talk to this chip, now, I can't have both of these low at the same time, can I? If I have 65 low and 52 low at the same time, they're both going to be accepting the data coming across these pins. Well, these are different chips, so more than likely, almost positively, they need different data, don't they? Right? So you can only have one of these on at a time. So you got to make sure when 52 is low, 65 is high. Okay? Only selecting one chip at a time. Okay. All right, great. When we select that chip, then we start clocking data over to the device. And this is a big thing to get into your head. Which pins are controlled by the master and which pins are controlled by the slave? Well, the master always, master controls the slave select, obviously, to select the pin. The master also controls the clock. Okay? So he's the only one that can produce the clock. So the only way data gets going to the slave is by the master sending something to the slave. Master out here, master controls the master out. But look, there is one that the slave controls, and that is slave out. So the slave controls the master in, right? Slave out, master in. So it will be sending the master data on that pin. The big thing I will always, so every time I come up to you and talking to you about SPI, when we're looking on the oscilloscope or we're looking at your source code, so you'll try to get this in your head, the only way you can receive data from the slave is if you send data to the slave. So I always say you must send to receive. What we'll be seeing when we start looking at the data sheets for our devices, especially, well, any device, but that MPU 9250 we're going to be looking at in homework, you're going to see sometimes, yes, you have to send. But when you're sending that data, sometimes you're receiving garbage. Who knows what the value is? It doesn't matter. But because of the way SPI is designed, whoever put it together, well, yeah, I don't know what company put it together. If you're sending data out, you're always receiving something back, but it may not be of any importance. So you'll see in my code, in your code, there may be times we send over data and we have to read it in, but we'll just put it into a temp variable and never use it. Because we have to read it to get it off the buffer, okay? But we can just not use it. So I'll call that a lot of times garbage data. Okay? Things that we just have to read off just so that we can read off the good data. Okay? When it comes. There'll also be some times when we can send anything over. We've got to send something. And usually when you send something and it doesn't mean anything, I just say send 0, which makes some sense. Okay? But you can send anything. Okay? Sometimes you just have to send anything in order that you get good data back from the SPI also, which is interesting. And you'll see that too. We'll see that in different code too. So that's where we're going with this. And we're getting a little ahead of ourselves, but not too much. The basis for our homework problem is just kind of look at these signals, okay? And try to understand what's going on when you send data, receive data. So, and we're going to see this on the oscilloscope when we get going with this in homework 3 and in lab 6, actually. I think, yeah, lab 6. Anyway, let's look at those plots over in the PDF file that you'll pull up from the, which one's PDF here? Right here. Okay, so let's look at these signals here. A little hard to see here, but that top one over on the left says master out, slave in. Top left is master out, slave in. Then this one, the next one is master in, slave out. And then the third signal is S clock. And the last signal is slave select. Okay? So the way this chip or this data that it looks like, we need to pull slave select low to get 8 bits of data. You see that? 1, 2, 3, 4, 5, 6, 7, 8 is what we're sending and receiving at the same time, because there's only one clock. Okay, and then with this chip, a lot of chips you can actually you can pull it high and then low again for the next 8 bits, or you can leave the slave select low for the whole time. Okay. Some devices want you to keep it low. It's just funny. You have to read through the data sheet, try some things, and see what works sometimes. So that's where we'll have to keep on thinking about that as we get to a device. But notice, for the chip to send us anything, slave select needs to be low. Okay? When slave select is high, no data is coming into us. Okay? Or out of us. Good. And then the clock. The clock here, what we're saying here by this dotted line, this is the edge. So a clock has a rising edge and a falling edge, doesn't it? Okay? The inventors of SPI, I wish I could go back in time and tell them, don't do this, just pick one. They decided with this protocol to allow for 4 modes. And it's really annoying. I wish they would just have picked one mode and everything would have been a lot, SPI would be that much simpler. But you can, the 4 modes is, the clock signal is normally low, starts low, and you read data, write out data on the low going edge. Okay? Or, this is mode 0, right? Yep, mode 00, I'll explain that. Mode 00, or mode 01, where the clock is normally low, and you read write data on the rising edge. So that's my dotted line right here to indicate that for you. Okay? Or mode 10, and so you got to look at the data sheet to figure out which mode your chip uses, unfortunately. Mode 0, I'm sorry, mode 2 in a sense. We had mode 0, mode 1, mode 2 is where the clock is normally high and you read write data on the rising edge. And then you can figure it out what it would be for mode 4. Mode 4 would be clock starts on the rising edge, clock starts high and we read write data on the low going edge. Kind of get that? Okay. I know, I don't like it. I don't like it. It's always a pain in the rear. And what's also a problem a lot of times is the data sheet isn't super clear which mode it is. They try to draw TI has one data sheet that I dug through, and they, according to the data sheet, it says it could be both mode 0 and mode 3 or something like that. I've never been able to get this chip to work in mode 0. It only works in mode 3 for me. And that causes, it causes little headaches. You have to figure out if your code's working right and all that. Now the good news is there's only 4 modes. You could try 1, 2, 0, 1, 2, 3 until it works too, couldn't you? And that, at least that's not a huge number of different modes. But you got to be careful. Anyway, so and what you do, and we'll go over this more in later lectures, but you go and look at the data sheet and they'll put up something like this. Not all the nice colors and everything. It'll look, let's see, I don't think I'll be able to pull up something quick, but you'll see the clock signal and you'll see your data. And you'll see, okay, it is normally high, and they'll show that in their timing diagram. So that's a good one. If you see that the clock is normally high, now you're down to 2 modes that you can use, right? Because there's 2 modes for normally high. If the clock looks like it's normally low, then there's 2 modes that you got, right? Either now it'll be clocking on the rising edge or the falling edge. Now, it's not as easy to see here, but notice here what happens here. The SPI is kind of smart. It uses both edges of the clock. Now, the important edge is the one I have dotted here. And see, at all these dotted edges, right, on this, for this mode at least, for mode 1.1, on this edge, I go up and I see what is the state of master in and what is the state of the pin master out. And you see here, since it's high, that means the master is outputting a 1 for that bit. Agreed? And if in here this is low, that means master in is the slave is sending us a 0. You kind of get that? Okay? And then we just do 1 bit at a time. Here we got to remember though, different from the UART like we did in homework 1, the UART sent the least significant bit first, if you remember that. SPI sends the most significant bit first. Okay? So the number you get, is actually like this says here, the least significant bit is the last one you get. Okay? And now the good news is the serial port knows this. And the serial port, SPI serial port, knows to put it in that order. And when you go read the results it's kind of not called results, it's just called the receive buffer. When you go read the receive buffer, those bits are already in that order. Okay? So it's not like you have to do anything to rearrange them or anything like that, which is good. But when you're looking at this and giving me the answer for the homework, you got to remember that it is most significant bit first. When you tell me the 8 bits or 16 bits, whatever it is, that are coming across to you at a time. And what I said, also notice what happens on the other edge. So in this case, you can see it right here. On the falling edge is when we read data, but we've got to move to the new bit, don't we? And so SPI on the opposite edge, in this case the low going edge, we read data. On the rising edge, if the next bit is 1 or 0, it transitions to the new bit. So the opposite edge transitions to the new value, right? So in other words, what happens let's look at this master in. When the edge goes low, we read in that 0. And also, it knows to get there, whenever it sees the chip select, it knows to pull the most significant bit or whatever, set the pin to the most significant bit right away on chip select. Does that kind of make sense? Okay? And so it starts out at 0 because that's the most significant bit. It's a 0. But then we read that, and then on this rising edge, if it was the next bit would have been a 1, it would have transitioned right here to 1. But since it's 0, it stays at 0. And again, transitions stays at 0. Transitions, middle here, stays at 0. But here, see on that rising edge, the opposite edge of what we're reading, it transitions to 1. Okay? Read, and then transitions to 0. Okay? So that is one way when you're looking at an oscilloscope and you don't have my nice dotted lines right there, that is one way to indicate to yourself what edge is it transitioning on, what edge is it reading the data, right? Does that make some sense? Okay. Now, that's where this little diagram comes in. This is out of the data sheet. Sometimes this is confusing the first time we look at it too, but this little guy that I copied, where'd it go? Right here. So this is out of a table, and actually the document I gave you, I put this little scratches on here. So what we have in our registers for the SPI setup, we have 2 bits. A bit that's called polarity and a bit that's called phase. Okay? And to set these 4 different modes, you can, 4 modes, phase 0, polarity 0 is mode 0. phase 1, polarity 0 is mode 1, right? And see what I'm doing? Mode 2 and mode 3. Okay? Now, only one of these modes can happen at a time. That's what gets a little confusing about this diagram right here, is that in their data sheet, is that they show you all those clocks, but really when you're transmitting data, it's one of these clocks, one of these 4. So that's what you keep in your mind. The other thing is, I don't like, but their dotted line, this is not my dotted line. I know, I just love confusing you, right? Personally, I think the dotted line should be on when you're reading data, right? Because you want to see if it's a 1 or 0. That's what we want to determine. We want to read what data is coming across. So it's easier to find on there. But this is the transition dotted line, right? This is the edge that the data is moving. So this diagram too, you'll see this in data sheets. Do you see what's going on with master in and master out here? This is saying by them crisscrossing at this point, this is just a general diagram. The diagram does not know if the most significant bit is 1 or 0. So that's why it's showing you it's transitioning either to 0 or to 1, is what that's saying right here, okay? So this could be a 1 or 0 bit, is what we're trying to say. Then we have a transition on the rising edge of this clock, and we get a 1 or a 0, obviously, right? And we read that on the low going edge. Okay, so my dotted line, as I said, goes to the bit, what the value of the bit would be. My dotted line is in the middle here of what I'm showing in the diagrams. Because what I want you to do is go look at this diagram, and that's what I want you to do in the homework. I want you to go look at, where did it go? PDF. I want you to go here and say, all right, what data is going across here? And I've also already given it to you, but I know I'm reading data on the low going edge, so I just take that low going edge up to here and see that it's a 1, don't I? I take that low going edge up to here and I see this is a 1. And I've done this all for you, but go up, that's 1, 1. Go up from here, it's 0, 1. See what I'm doing? That's how we determine what data is going across the serial port. And write it down and then give it the answer to me in the homework. Okay? For the baud rate, it's the bit rate. So this amount of time from a completion of a clock, a full clock cycle, is the bit rate I'm asking for. You're just going to estimate it. It does not need to be exact. I give you the units right here. You can't even see them, but just guesstimate. So it's from 2.5 to 3. I think that may be 10 to the negative third. I don't know, whatever that is. I can look here. That is 10 to the negative fourth. 10 to the negative fourth. So this amount of time, you kind of guesstimate what that is in there, right? And give me a bit rate. Agreed?